Okay, so I sort of reversed the order a little bit, and I want to do something that's probably more new to most people, and then do something more familiar later in the next lecture. This later is only the next lecture, right? So we want to show that, I want to show that you can find low-rank approximations to a matrix from just having a length squared sample, right? Just like we did multiplication. We'll use multiplication again. We keep using that. And we did compression, right? So just like that, we can do SVD or low-rank approximation as well. So we saw that SVD is the way to do the best low-rank approximation, right? That's what you get out of SVD. You truncate it. You get the best possible approximation of every rank. We won't shoot for the best possible approximation. We can't do that because we are only going to sample. We'll shoot for a good low-rank approximation. Good in a sense will relate to the best. In comparison to the best, it's not too bad. That's what we want to show. The advantage will be the time will be it'll be much faster. You'll have to do essentially SVD on a very small matrix, and from that you'll get everything. So that's the advantage. By the way, one thing I did not say is length squared sampling can be applied to infinite matrices as well. I didn't go into that much. So if you have infinitely many columns, but of course you have to have a convergent sum of squares, otherwise you can't do it. Then you can sample a finite set, the infinite number of columns, but finite dimensional. You can sample a finite set and all of this goes through, but we didn't see that. So that's another advantage of doing this as opposed to full SVD, because if it's infinite, then full SVD is impossible, right? Okay, so SVD, so again, I'm just repeating this. SVD is the best approximation of each rank. What we will show is that if I pick a length squared sample of just rows of A, and I do SVD on R, just on that matrix that looks like that, that gives you a decent approximation to the SVD of A. Now you have to be a little careful. A is, the dimensions are different, right? So you have to relate the SVD of R to the SVD of A in a nice way. We'll see that. Okay? In fact, most of the central result here will not be anything to do with length squared sampling at all. It'll have to be, it's a purely matrix perturbation result, and we'll prove the following. If I get a good low rank approximation of R, provided R transpose R and A transpose A are close. Now, just nice to recall the dimensions of those. So A is, if A is n by D, A transpose A is D by D, and so is R transpose R. R, only some number of rows have been picked, so it's little r by D, but R transpose R is also D by D, right? And maybe, again, just a picture. So if I have this as my A, the rows, I sample only a few rows. A transpose A wants to take the dot product between every pair of columns, right? And R transpose R just takes the dot product of the sample in the sample rows. Right? I mean, just writing a picture of it. So they are the same dimensions, so it makes sense to say that they be roughly equal. And what we will actually show is the following. Again, the dimensions are different, so the relation will be this. If I restrict A as a linear transformation to the space spanned by the top few right singular vectors of R, that's a good enough approximation to A. Now, that's the right dimension. So the right-hand side dimension of R is right. Okay, this is what we'll show. So the main result really doesn't have to do with length squared sampling. It just has to do, again, with this. In a way, I perturbed A. You can think of it as a perturbed A transpose A to get a slightly different matrix R transpose R, except it's a lot simpler because it's a product of two matrices which are smaller. If the perturbation is not bad, then this is true. We'll prove that. Okay. And then this is, again, purely a matrix perturbation results. There's no probability involved in that part. But as we saw, we will see, again, we'll recap, that if I have a length squared sampled R then A transpose A equals R transpose R, roughly, approximately. And that's the familiar matrix multiplication theorem. So if I were multiplying the matrix A transpose by the matrix A, I might do that by picking some columns of A transpose, which are rows of A, and that's my R transpose, and then pick the same rows of this A, which is R. Okay? And matrix multiplication theorem, in spirit, I mean, we'll quantify this. In spirit, told us these are roughly equal. And this perturbation result is going to tell us if these are roughly equal, then in fact SVD of R will give us SVD of A. Now, let's recall that R itself, I want the right singular vectors of R. R is, the right dimension is very high, right? Because R is like this. This dimension is still D. So that seems to be a D-dimensional problem. But observe that R is only R by D. I could take R transpose. Okay, that's a small matrix. It's a little r by little r matrix. That's got only this many rows and this many columns. I can do, I can find its right singular vectors of R now. I'm sorry. The left singular vectors can be found from this. These are just eigenvectors of R transpose. We saw that the spectral decomposition of R transpose is related to the singular value decomposition of R. So the left singular vectors, they can be found. And then you find the right singular vectors by folding them in, right? So we saw that if I take a matrix A and multiply on this side by the right singular vectors, I get the left singular vector. And vice versa. So I want, so I have to do, the essential computation I have to do that answers that question is that I have to find spectral decomposition of a very small matrix. Okay? But then I have to do some matrix vector multiplications. Those are simpler. Right? Okay, this is the gist of the story. So first I'm going to prove the matrix perturbation result. And I'll do a self-contained proof that'll involve some classical result which we'll go over. So singular values and singular, but here's another point that'll be nice to make, which is an important point from linear algebra, right? So this is also something standard, but I want to make this point. The perturbation inequality we'll use is called the Hoffmann-Whelan inequality. It will say that if R transpose R is close to A transpose A in Frobenius norm, then the singular values of A and R are close. We'll prove that. Okay? So I've made a small perturbation you can think of A transpose A to get R transpose R. If the perturbation is small enough, the singular values don't deviate too much. Okay? That sounds very plausible and true, and in fact it's true. So now you can ask, what about singular vectors, right? So we really want a low rank approximation of A, and that would be possible intuitively if we get a good approximate top singular vectors of A, right? If I get the top few singular vectors, may not be exactly, but approximately, that should be good enough to get a good low rank approximation of A. If I get them exactly, I get the best possible. If I get them approximately, I should get it approximately. Now, if my inequality here, Hoffmann-Whelan or any other inequality, actually guaranteed that the top singular vectors of R and A are close. So if this is small, would imply that R and A have very close singular vectors, then A will be very simple, right? Then that would say, find the singular vectors of R, they are close to singular vectors of A, and they give me a good low rank approximation. Okay? Unfortunately, that's false. This is false, right? Even though perturbations don't change singular values too much, they can completely change singular vectors. Okay? Singular vectors are singular. That's maybe one reason to call them singular, but singular values are not. So multiple singular vectors or points of discontinuity of singular vectors. Sorry, multiple singular values. That means, like multiple eigenvalues. There are many eigenvectors corresponding to the same eigenvalue, then it's called a multiple eigenvalue. These are the multiple roots of the polynomial, right? Similarly, if you have a singular value that has associated with many singular vectors. Then there's a discontinuity. I'll elaborate, but I'll give you an example first. But before all that, please do recall from linear algebra that if you had ties for, say, eigenvalues, you have a bunch of eigenvectors. They form an invariant subspace. And I could have chosen in linear algebra, right? I would choose any basis of the subspace can be my eigenvectors. And that's the reason for the discontinuity, right? So if you flip things a little bit, you might flip from one basis to another. And so that's a complete flip of the eigenvectors. So, and the simplest example is this, right? So if I have a matrix 1 plus epsilon 1 minus epsilon 0, 0, at epsilon equals 0, there's a discontinuity of the singular vectors, not of the singular values, or of the eigenvectors, but not of the eigenvalues. The eigenvalue is continuous at epsilon equals 0, right? So it's the eigenvector that's discontinuous, because if epsilon is positive, the eigenvector is the first unit vector. Epsilon is negative, it's the second unit vector. So it flips completely, right? So, but you know, the point to remember is that low rank approximation intuitively is not discontinuous, right? If I take the singular vector of a slightly worse singular value, so suppose I had this picture, and epsilon was positive, right? So the eigenvector or the singular vector is the top one, but this is a close by eigenvector with eigenvalue 1 minus epsilon instead of 1 plus epsilon. So if I took this vector instead of that, intuitively I shouldn't be very far off, right, in the approximations I get. That is true. I am badly off if I want exact eigenvalues. If I want Ax equals lambda x, I'm not going to get it if I took this instead of that, right? But I'm okay if I want just an approximation. So that's what we'll use. Okay. So presumably this point is clear. I'm just recapping, you know, jogging your memory on linear algebra about continuity of eigenvalues. Eigenvalues are continuous. Eigenvectors are not. Now, this is just for your information. I won't prove this. In fact, it is true that at points of continuity, at points where this discontinuity does not occur, eigenvectors or singular vectors also behave nicely. Okay? So these are harder theorems. So when there is a good gap in singular values, so discontinuity occurred when two singular values were the same. Okay? Preventing that means singular values are quite different. So if there's a gap between successive singular values, then it's also true that the singular vectors behave nicely continuously in a quantified way. So not only continuous, but Lipschitz, right? That's what this is saying. Singular vectors of a perturbed matrix are close to singular vectors of unperturbed. These are harder theorems. Sorry? Sine theta, these are called the sine theta theorems or Vedin's theorems. They are due to Vedin. The simplest versions are due to Kahn, and they're called the sine theta theorem. If you want to look it up, you can do that. Yeah, again, I won't prove these. We don't need that, right? So we saw that this says I don't need these theorems, because low rank approximation, I'm okay if I missed by a little bit the singular value. Okay, so just a technical fact. This is just a definition of the restriction of a linear operator or just a linear transformation to a space. So if you have a subspace V spanned by this basis, and I want to take a linear transformation A restricted to A, restricted to V, I just say the restriction is A bar, which is that. It's restriction in the sense that A bar x is the same as AX if x belongs to V, and 0 if x is orthogonal to V, right? And both are quite clear. I mean, the 0 is completely clear. If x is orthogonal to the space V, it's orthogonal to all these W's, so it's 0. And the first one is just a little manipulation, right? So we have A bar x. Now, x belongs to the space. So x can itself be written as sum of alpha t wt. And then you expand out A bar, and you get, we've done things like this before, times this quantity, right? I'm going to put a t prime here, alpha t prime wt prime, and you see that these are all 0 unless t equals t prime. So those terms go away, and only the terms that W2 remains. So then you just get alpha T WT, and that's equal to AX. Okay? So restriction just means it does what A does in that subspace. Orthogonal just zeroes out. Orthogonal is also null space. Okay, now the statement of the main theorem. So we'll state the main theorem, which is, as I said, purely a matrix perturbation result, and then we'll prove it. Now R is not necessarily length squared sample. It's just any matrix which is R by n. It is not even a submatrix necessarily, right? R has no relation to A. Okay? So it's for every pair of matrices R and A this applies, as long as the n is the same, right? So if V1 through Vk or the top k right singular vectors of R, so I want to say if I found the right singular vectors of R, that gives me a good approximation to A. Okay. Then the assertion is, conclusion is, the restriction of A to the span of this is approximately A in both Frobenius and spectral norm. And of course, that won't be true for all R. R can be arbitrary, but the error involves how different R is from A in this sense. And here's a precise statement. Two precise statements. So spectral and Frobenius norm. So let's go over these. So I should say that. So I take A. This from the last slide is the restriction, is that thing, is a restriction of A to the span of that. That's written verbally, right? This is in symbols. That's what the last slide said, right? Okay. In Frobenius norm, that's less than or equal to A minus AK Frobenius norm squared. Now, AK, I'm sorry, I used a slightly different notation last time. I said A sub K, but this is also just the best rank K approximation to A, which we saw last lecture obtained by SVD, right? So the best you can do, you cannot do better than that, right? You'll be worse by a little bit, and the little bit is root K times the Frobenius norm of that. So just make sure the scales balance. I take the square of the Frobenius norm of A, and this is like the square, right? I've taken A transpose A. So the dimensions balance, right? Just okay. So that's statement number one, and also in spectral norm, this is the best possible, because again, SVD was the best you could do in spectral norm, and the error does not have a root K. It has just the spectral norm there also. Not Frobenius, but spectral. So both of these are spectral norms in this case. Okay. So again, this is repeating what I said. A minus AK squared is the best possible error with exact SPD. We cannot beat that. That's the best we can do, right? And this second term is the error. That's a little bit more. Okay, and we get that. Now, one note I should have said, perhaps that I should put on the slide maybe, but I can tell you. So more recent theorems. But these are based on sampling. Actually can give you the right-hand side, which is better. So these are called relative error approximations, because so A minus AK, right? If you were going to use principal component analysis, for instance, this would be hopefully very small. So you would use it for matrices which are very close to being rank K. Okay? So if this is very small, this may be actually much bigger. So this error term is pretty big if you did length squared sampling. There are more complicated sampling schemes for which you can actually show these things, which are called relative error bounds because the error is relative. And so I have a survey paper in which I also have these things, but we'll only prove this, right? We'll only prove with this absolute error. Okay. I can give you references to this. So again, this is how far you're worse off than the best you can do. Okay. Now, one thing that's instructive before we leave the statement of the theorem and go to the proof is, this theorem is also true for any r. It's true in particular for r equals 0 and n. It'll be nice to see what they say to us. What does r equals 0 say? That means I pick no rows in R, either probabilistically, otherwise I pick no rows. So R transpose R is 0, right? So this is 0, and there's no V's. So this is also 0. So you get A squared, right? And I should have said, excuse me. So I should have said, no, I'm sorry. This is true for all k. So I could back off a minute. So if R is 0, then there's no singular vector. All of these are 0. So you get A f squared here. You get A f squared plus a little bit more. This is positive, right? So that's okay. It's not saying very much. You don't expect it to say very much. What about R equals n? That's also an interesting case. I meant to say R equals D. I meant to say all the rows. Okay. So R equals the total number of rows of A. What's a possible R then? A possible R is all of A. So if R is all of A, this is 0, and this is 0, right? So still we are just saying 0 less than or equal to that. I'm just saying these things as a sanity check. If R equals 0 and n, it's still true, but they won't be saying anything interesting. It's for other values of R that you expect this. The proof will use the Hoffmann-Wheeler inequality, which I'll prove first. So I'm going to spend a little bit of time proving that. There are many proofs of that, and this I think is one of the simplest. We'll have to do a little bit of combinatorics here, but we'll prove that, and then I'll go back to proving this. Okay, so the moral of the story is for any R, you get a decent approximation in spectral and Frobenius norm. So, okay, so for this I need some technical results for the Hoffmann-Wheeler inequality. So you have two sets of real numbers, A1 to AN, B1 to Bn. These are going to be singular values of the two matrices, but later. Right now they're just real numbers. And the A's are in decreasing order. Then the assertion is the permutation that minimizes the difference between AI and the B at the permuted spot. So I'm allowed to permute B in any way, and I want to minimize this, right? So intuitively, it's obvious that the best I should be able to do to minimize that is also bring B's in decreasing order, because A's are in decreasing order. If B's are also in decreasing order, you would expect that to be minimized. Right? So usually the proofs of these are all very simple, and here is a proof usually for such a statement. This statement is if B was not in decreasing order, so let's say the I plus first, if they're not in decreasing order, there must be adjacent ones which are in bad order, right? If B was not sorted, there's a pair that's adjacent, not sorted. So you have that, and if you just swap, you'll improve. So you can check that. So it's just a simple check. Okay. Now we have to use another nice theorem called Birkhoffs Theorem that says every doubly stochastic matrix can be written as a convex combination of permutation matrices. Did I define that? No, I didn't define those terms, so maybe I should just recall those terms. So doubly stochastic means non-negative entries, all row and column sums are 1. All of them. So a matrix with this property is called doubly stochastic. Okay. and square also, I should say. I guess it doesn't follow. Right? And then the term permutation matrix just means what, it's permutation matrix is just got 1, 1 permutation matrix. So there's a permutation, right? So AI, Fi equals 1 for some permutation F. No, I should say this way. There exists a permutation F such that this is 1 and equal to 0 for all other entries. Okay, this is a diagonal matrix or any permutation. There are a lot of n factorial permutations, right? So Birkhoffs theorem says every doubly stochastic matrix can be written as a convex combination of permutation matrices. I won't prove that, but I'll just assume that. Okay. So when AI and BI now are both in decreasing order, according to this, right? The minimum value of this quantity, AI minus BI squared, AI minus BJ squared, Xij, I'm going to try to minimize that over all x's which are doubly stochastic, which form a doubly stochastic matrix, right? Is attained at a permutation matrix first. So why is that? Why is the minimum attained at a permutation matrix? Because of the convex combination, right? So if the minimum is attained at some doubly stochastic matrix, you can always write it as a convex combination of permutation matrices, and there's a linear function in the Xij, so it should be attained at one of the permutation matrices. And secondly, since the identity permutation is the min over all permutations, this is attained by the identity, right? So we saw that the permutation that minimizes is the identity. That was this part, and this says that over all stochastic matrices, the minimum is attained at a permutation matrix must be the identity. Okay. So we'll come back. We're going to use this in the next slide, but I may have to come back and recall this for you. So now Hoffmann-Wieland. Oh, I see. No. Okay, I guess I don't have it. I have it all displayed in one shot. This is the proof of Hoffmann-Wieland now that we have Birkhoffs theorem and all that. So if you have two real symmetric matrices with lambdas as the eigenvalues, I've arranged lambdas of both matrices in decreasing, in non-increasing order. Then the assertion is the lambdas are close, right? Provided P and Q are close. So if P and Q are close, the lambdas are close, right? The eigenvalues are close. Again, this is continuity of eigenvalues. Eigenvectors are not continuous, right? So you take the sum of squares of all these things, that's less than or equal to the Frobenius norm of the difference between P and Q. Okay. So how do we prove that? So I'm going to go over, while going over this, we'll recap some linear algebra as we go along. So I'm going to write P as U d U transpose, and this as V d prime V transpose. These are spectral decompositions. And just to recall, so U columns of U or eigenvectors of P. The P and Q are symmetric, right? Eigenvectors of P, so they have spectral decompositions here, right? So, and V is columns of V or the eigenvectors of Q. And so we have been using a slightly different notation, but D is diagonal, D prime are diagonal, they are the eigenvalues. So U d U transpose, if you think about it, is the same as saying lambda I, this is for P, so lambda I of P, U column I of U. So column I of U, I wrote it this way before, so let's write that. And that is UI transpose, U transpose I, rho I of U transpose. I'm just expanding the matrix. This is just a matrix notation which we haven't used before, but more standard than the one notation we've been using, right? So this is just the outer product of columns and rows. They sum up. It's worth checking that these two are the same, and these diagonal searches comes like that. Okay. Now, what we know is that the columns, the eigenvectors are orthogonal. The columns of U and V, U are orthogonal or orthonormal. And in matrix notation, that is just going to say that U transpose, no, sorry, I was going to say U transpose U is the identity. And V transpose V is also the identity. Actually, the other way as well, because if you have a full dimensional orthonormal matrix, then the rows are also orthogonal. Right? So if you have, in n space, you have n columns which are orthonormal. The matrix also has orthonormal rows. Not true if it's less than n, but if it's n, that's true. So in fact, UU transpose is also equal to VV transpose equal to I. Okay, bunch of linear algebra will recap, and we'll use that. Okay, so so these are spectral decompositions with eigenvalues arranged in non-decreasing order in both cases, and I'm going to do something that it looks, it's pulled out of the hat. So I'm going to take P minus Q, multiply by U transpose and V on the two sides. I get U, I'm just expanding this out. U transpose U, D, and so on and so forth, and I get that. Now U transpose U is the identity, right? It's one of these things. So that goes away. I get D times U transpose V, and again, V transpose V is the identity. That goes away. You get that. Now, these are orthonormal things, so they are all length preserving. They don't change the Frobenius norm. Okay, it's invariant, Frobenius norm under these transformations. So I get this is just, I'm taking the Frobenius norm of the whole thing here squared. That's the same as P minus Q squared. And that's the same as that, Frobenius norm squared. And that's the expanded version of this. Now, why is just quick check that that is correct. That's just algebra, but let's check that. So I want to know what the ijth entry of this is, right? Well, ijth entry of this is dii1, sum over I1, U transpose I1, I2. I'm just writing them down, and V I2 J, right? Sum over I1, I2, and J. I1 better be equal to I, otherwise it's 0. So this goes away. This is I. Okay, and so you get dii is just, I call that di. Okay, and this is just U transpose V's ijth entry because I sum over I2. This sum over I2 goes in there, and I get that. So that I've just done the algebra for the first one, right? And this is similar, just U transpose, same U transpose V. So anyway, so you get that. Now U transpose V is also orthonormal because U and V are. You have to check that. Another linear algebra fact, maybe I won't check that. They are orthonormal. And so the rows and column sums of the matrix, rows and column sums, column lengths are 1. That means the sum of squares is 1. So if I take this matrix, that is doubly stochastic, right? If I put this. Then I use the theorem from the last slide, right? So this, so di minus di prime squared, these are eigenvalue differences squared. There's something that I want there. That's what I want, right? Those are weighted by a doubly stochastic matrix, and the minimum is attained when I put the identity there. That's what I showed in the last slide, right? So I put the identity, so only the cross terms go away, I and j not equal go away, so you just said I and I for both d and d prime, and you get that. Okay, you do have to check all the intermediate steps. So this is that quantity, right? And I started from that side. Okay, so that's Hoffmann-Wieland, and let's go on to our theorem. Okay, so V1 to Vk. So now we'll have to do a little bit of algebraic manipulation, unfortunately, to get to the theorem, but it's not too bad, I hope. So we compute, we take V1 through Vk. So the theorem said, I'm going to restrict A to the space spanned by the top k singular vectors of R. So these are the top k singular vectors. I'm going to make a full basis out of it, right? You can always complete a basis orthonormal set. So I would like to prove this is small. So this is A's restriction to this. I like to prove this is small. And I'm going to pull something out of the hat. I'm going to pull this out of the hat and subtract. So again, unfortunately, this you'll have to go through some manipulation here. In fact, I wanted to prove this is small with respect to this, right? So maybe I should go back to the theorem for a minute. Yeah. So I want to prove this is small comparison to that. I just brought this over to this side. Okay. So I've taken this minus that. I want to show that small. So I have that, and I'm going to expand that. Okay, so this a few more lines of proof. So this is A restricted to a particular subspace. Okay, and that's always the Frobenius norm of that. The difference is A minus that. You have to prove that, right? But I mean, a simple proof of that is just by the completion of the basis. So, okay, maybe I should write that. So, AF squared is just equal to A times VT squared. Right. So the Frobenius norm squared is the sum of the row squared lengths, and you can write the matrix. Norms, nice norms are always invariant, whatever the basis. So I choose Vt as the basis, then you'll get this. And I've subtracted out the first k, so you get only k plus 1 to what's left, right? So that minus that. You also have to prove that that is equal to that. Again, similar proof. I won't do that. These two cancel out, and you get that minus that. Okay. So that I have to prove is small. Few more tricks. So AK is the best rank K approximation. So that came from SVD, so that's just the SVD theorem we proved. We proved that SVD is the best approximation, so you get that. What about this? You can see that that's just equal to AVT squared, right? See, all of this is not true if it's not orthonormal. Everything uses all these facts, so that's true. So now I want to write that is equal to, this is the same as what I had before. Here's another trick. I'm going to take AVT squared, that is, I mean, the first, here's not a trick, it's just simple. That's just equal to VT transpose A transpose AVT, right? There's a length squared of a vector that's equal to its dot product with itself. Again, that's not a trick. But I'm going to add R transpose R and subtract it. Okay, that's okay, I'm adding and subtracting. I've done this several times. I did it last time too. And now what do we get? Now we get this is this squared. Here, Vt are the singular vectors of R, so those are just the singular values of R. So that's a difference. Okay, so I'm going to use this difference and bound it using Hoffmann-Wieland. I'm coming to that. But that's this term and this term. I still have to deal with this term. I've rewritten that. I've not dealt with it yet. So now this is less than or equal to k times that, because for each vector v, this quantity is at most the spectral norm of that. Okay. Now we define spectral norm slightly differently, but you have to, so we defined spectral norm of A as the max over all v of AV. But it's also true that the spectral norm of A of a symmetric matrix A transpose A minus R transpose R, this is symmetric. They're both, so the difference is symmetric, For a symmetric matrix, the spectral norm is the max over all V of V transpose times the matrix times V. Okay, this all, at the end of this day, this gave me a k, but I want to get a root k. If you're happy with k, you're done. So I'm going to work a little bit, one more slide of work to get a root k. So for this, we have to use Cauchy-Schwarz. So we take that. The reason I'm doing this proof is partly, its algebra is uninteresting, but hopefully it'll jog your memory on the linear algebra that you might have forgotten. So for this, we use Cauchy-Schwarz to assert that that is less than or equal to that. That's just the sum of k real numbers. These are real numbers. So that's less than or equal to the sum of squared, then a square root, and then a root k at the top. Now what is this? So this is, so I claim that that's at most the Frobenius norm. Why is that? The Frobenius norm is invariant in the change-up basis. So in the VT basis, right, these entries are the diagonal entries of that matrix. So we have matrix A transpose A minus R transpose R. If diagonal entries in that basis are just this, I'm taking the sum of squares of the diagonal entries, which is at most the Frobenius norm. I'm throwing away something because the off diagonal is not being counted, so that you get that. Okay, we are still to bound that. For that, we use Hoffmann-Wieland. So by the way, Hoffmann-Wieland is only for symmetric matrices, as stated. So I had to do some of these machinations to get to the proper symmetric matrix. So we use another Cauchy-Schwarz, and then plugging all this in, you get the Frobenius norm assertion. Turns out the spectral norm proof is not much harder in this case. Yesterday it was harder, but today it's not so bad. Bounding the spectral norm. So we have only a couple more things. Bounding a spectral norm. For the second assertion, that's a spectral norm assertion, that's all. The top singular value u of this must be orthogonal to the span of this, V1 through Vk. So because I subtracted out the action of V1 through Vk, if you had a component along this, it would make just 0, right? So that's not interesting. So you might as well be assumed to be orthogonal to this. So this product goes away, and you just are left with AU. So, so again, we do have to do some work. So this is what I wanted to bound. So again, this is A. This is a restriction of A to that subspace. I want to say the difference is small. And since the top singular value is U, singular vector is U, so I get that. I get that. Now this trick again, I have A transpose A. I'm going to add and subtract R transpose R. It's same trick. And that's because I know how to bound this. That's this. And this quantity, U, was orthogonal to the top k singular values. I'm sorry, singular vectors of R. These are the exact singular vectors of R. It's the top k. So this is at most k plus 1. So we again saw that. So it lives in the space of the k plus 1 and later singular vectors. Therefore, you get the best that. Okay. So we're not done yet. So that's that same written like that. Now I have that. I'm adding and subtracting sigma k plus 1 squared A. This is, we know what this is. How about this? So I'm going to say that's also at most this. Okay. And that is using Weil's inequality. So let's remember that again. I'll write a short proof of this. This is one of the many inequalities in linear algebra. But so it says for a symmetric matrix, like R transpose R is, I take the k plus first or any eigenvalue in decreasing order. Eigenvalues are in decreasing order. That is at most, I've written in a particular way. Let's write as inequality here. So it's saying lambda k plus 1 R transpose R is, for instance, less than or equal to lambda k plus 1 of a different matrix, A transpose A, plus, I've written that. So that's, I would like to say this is the top eigenvalue of that, but it's the top eigenvalue in absolute value, right? So that is that side, and there's a symmetric inequality. How do you prove something like this? So we prove it by taking, well, we have to use min-max theorems. I guess I didn't write. Okay, so we don't prove it. Well, you can look up a proof. To prove this, I have to use min-max theorems, which I just realized I didn't prove. But you know, you can look up any standard book, and you'll have this inequality. I do have to have symmetric matrices, right? Otherwise, I have to be a little more careful. But here we do. And that is telling us that this difference, that's this minus that, right? The difference between these two is bounded by this at most. So that's got a factor of 2 plus sigma k squared, sigma k plus 1 squared. Okay, so that's the end of that story for proving the main theorem. Okay, and by length squared sampling, we can get an R. We can get it by any other means, right? As long as this is small, for which it's enough to do SVD on that, R transpose R. Okay, now I want to take a step back and figure out what we have done in terms of time, how much we have saved, right? Okay, so this will also recap the overall proof and sort of the algorithm behind it. So what we needed was the right singular vectors of a smaller matrix R, and for that we can do SVD. I remarked on this first in the beginning, but I want to recap it because now we have an algorithm, and we'll analyze the running time. We can do SVD of R transpose, which is a small matrix, R by R matrix, and that gives us the left singular vectors of R. So the eigenvalues of this or the left singular vectors of R, because you know it goes on the left of R or the right of R transpose, which is the same as left of R, from which we get the right singular vectors by just multiplying once by R. And I'm going to figure out how much time all this is going to take, right? That's the story. So this how just meant multiplying left singular vectors by R to get the right singular vectors algorithm. So we pick R rows. Now I'm going to give you a length squared sampling version. You could do it by other means again. Pick R rows of A by length squared sampling. Scale them so that for the resulting matrix, expected value of R transpose R is A transpose A. Remember, this is going back to the beginning when we did length squared sampling. We said to make it unbiased, you have to scale it. So you pick these rows, right? And to make the estimator unbiased, you had to scale it by the. You have to scale down by the probability you picked. Okay. So unbiased just means the expected value is right. Okay. We already did this in the beginning. Now find R transpose. So I picked R. The expected value of R transpose R is A transpose A. But I find the other thing, R transpose. Find the left singular vector by spectral decomposition. Pre-multiply R by the left singular vector to get the right singular vectors of R. Okay, all that is routine. And then you return A times this as the implicit LRA, meaning if I don't really want explicitly what the low rank approximation is, and that is useful sometimes. I'll try to show you one instance where it's useful. You do A times VT transpose, or if you want an explicit one, multiply out and return. The time required, if you, okay, I should mention one thing. We didn't do many algorithms here, but if a matrix is sparse, lots of big matrices have very few non-zeros, and you don't write down all the entries of the matrix. You only write down a linked list of non-zeros. So that's a general trick. Maybe I should write that. So a sparse matrix, we have few non-zeros. One example is the hypertext linked matrix of the web. So it has X billion, right? It's a matrix, right? But each row has only about 10 non-zeros. So you write it down by having basically a linked list of non-zeros. Linked list of non-zero entries. It just tells you where the next entry is and so on. So you don't write down the zeros. You basically have space proportional. You have space, which is order. Here's a piece of notation that's now become standard. N and Z of A, which is the number of non-zeros of A. Number of non-zeros. So in fact, several, I didn't mention many algorithms, but there has been some effort, and people have now made many of these algorithms depend fairly benignly, linear quite often, on the number of non-zeros only. So in the case of the web matrix, right, if you had an n squared algorithm, that will be pretty bad. But there aren't n squared entries to be read. So the argument is that this can all be done in time proportional to the number of non-zeros, provided the R and all are constant. So one way to see that, so this is an advantage of sampling algorithms, by the way, over iterative methods or any of these methods. Standard numerical algebra methods, unless you're careful, will fill out non-zeros. The matrix will become dense, and then after a few iterations, and then you're in trouble. So these don't happen with these kinds of sampling-based algorithms, just because you work only on a sample of the matrix. So if P is the maximum number of non-zero entries in any row. In this case, P is 10. Now, it's not true that the maximum number is 10, but pretend that was the average, then it would be 10. So the first step can be done in 2 passes from external memory. So we saw that, how to sample going through the matrix twice from external memory. Right? You compute the probabilities one step and the next step. You pick them out. Then you find RR transpose. And now RR transpose is R rows multiplied by R rows. So R squared multiplications, but each only P time. Right? There are only P non-zeros. Dot product of 2 vectors with P non-zeros only takes P time. Spectral decomposition can be done in R cubed time or better. R is to be thought of as a constant, right? And P as well. So multiplying the k left singular vectors of R. So this gives you the left singular vectors of R. The right singular vectors can be found in time k times R times P. Okay? So you do take time dependent on n for reading through the entire matrix, but after that the times are not. Right? Unless you want to do this multiplication, then you have to go through the whole matrix once more. Okay? So roughly the time is linear in the number of non-zeros. And that's typical. We didn't do this kind of analysis before, but it's typical of these sampling methods. Okay. Now, I want to do one more slide and then tell you something which I didn't put on the slide. So I mentioned in passing earlier on, right, SVD requires only finds the best fit line through the origin, right? Subspaces always pass through the origin. It only finds subspaces through the origin. Okay. Now, you could have data which is nowhere near the origin, and then this is a big restriction. So here is the origin, and all your data could be here, and the best fit line might be like this, but you might end up finding this. Right? So you don't want to do that. How do you avoid doing that? So First, the definition of affine space of dimension k is just a translation of a k-dimensional space. Translation just means, so this is a vector space V. V plus x translation just means the set of u plus x, u belongs to V. Okay, I mean it's just moving like that. If it's orthogonal perpendicular translation, this is an x. It just moves out that space. It's also true that this x also is a good, right? You can translate this by this vector or this vector, you get the same thing. All that matters is what the perpendicular component is. Okay, that's just a definition, right? That's called affine space. So the lemma I want to prove, which is fairly simple, is the best fit affine dimensional affine space of any dimension passes through the centroid of the data. The centroid of the data, you have data points A1 through AN. Centroid C is just what you think it is. These are vectors. It's just average, right? Average is going to mean component-wise average. Just add them up as vectors and divide by the total number. Okay, so the proof is that if it's not the case, if you had a best fit subspace which didn't pass through the origin, it's a contradiction. You're going to gain by translating it to contain 0. So first let's prove this. So suppose you have real numbers A1 through AN, and I want to choose an x to minimize sum of squared distances of AI. It's not difficult to see that the centroid is the right thing. I mean, this also comes up in, defining variance from mean and so on, right? So proof, okay. So let's quickly go over the proof because this is typical proof that's used in many places. So I'm going to expand AI minus x whole squared. So I write it as AI minus C plus C minus A. Oh, I'm sorry, that's not A, that's C. No, C. Sorry, that's all right. C minus x, that's x. Okay, that should be an x. There's a cross term that I omitted because it's 0, right? So there's a term. So there'll be 3 terms when I expand the whole square. So I'll also get a term, sum over I equals 1 to n, the twice AI minus x times, AI minus C times C minus x. This is 0 because C minus x comes out, is a constant, is independent of the AI. 2 also comes out. Sum over I equals 1 to n. AI minus C, this is 0. Right? So that goes away. So you get that. That proves that for the case of real numbers, right? Because this is a non-negative quantity, and the best value you can have for it is 0. And 0 means x equals C. Okay. That's the lowest value, x equals C. That's what we wanted to prove. Same thing is true for vectors. Okay. So I want to prove this for vectors, actually. So AI minus x, I want to minimize the sum of squared distances. Okay. I'll come back to how you apply it to SVD. So I write it as AI minus C plus C minus x, plus I also put the cross term here. Cross term is AI minus C dot product with C minus x, right? That's dot product. I'm just using the fact that length squared of a vector is dot product with itself, and it's the sum of 2 vectors. If you expand it, this is what you get, and that term is 0. Again, C minus x comes out, even though it's a vector. The sum of these is 0 because sum of AI equals C. C is the centroid, okay, like it was for the real numbers. Okay, so how is this used with SVD? So if you want to find the best line that fits the data rather than the one going through the origin, you could just as well find the centroid. Okay, that's simple enough to do. Add all the data points and divide, take the average, and then subtract that from each data point. Subtract the centroid from each data point. Now the centroid becomes the origin, so there's no restriction in assuming that your subspace has to pass through the origin. Okay, so SVD will find the best affine space if you did this. So for a bunch of applications, you do that. So okay, So I think that's all I have on the slides, but I want to close by I take a few more minutes to say two more things. Okay. So far what we saw was that we had a matrix A, we do row sampling to get R, and we reduced by this process finding SPD of A to basically SPD of R. We could we further reduced it to R transpose, but this is in spirit what we did. So you can ask now, I can now take R, do column sampling on R, and reduce it to a really small matrix. Now can repeat, that is, I do column sampling on R to get an R by R matrix W. And intuitively, I should be able to reduce SVD of R to finding SVD of W. Right? I mean, it's just a symmetric version of that problem, except columns instead of rows. So this is true, but the proof is much more complicated. And the trouble happens because things go wrong when singular values are close to 0. So if somewhere in this process we have to worry about singular values that are close to 0. So this is true but complicated. I would say actually much more complicated, so it's not simple at all. But the moral of the story is, by doing the sampling twice, you finally were left with a constant size matrix, both rows and columns, constant number. And that's all that you need to worry about, okay, in some sense. Okay. I mean, that was true when we do RR transpose, it's a small matrix, but we'd had to find RR transpose for that. So we don't have to do any computation on big matrices except to sample. That's what this is going to tell you. Now, in practice, however, I'm not sure this has been used as much as row sampling has been used quite a bit, but both sides, I think it's too expensive still, although I'm not current on the state of the art. But to do that. Okay, that's one thing I wanted to say. The other thing also I should have put up on the slides. I'll just say that. So our error bounds for length squared sampling always had, or generally had, on the right hand side. Not every one of them. There was one today where I had only the spectral norm, but this is what I generally had on the right-hand side, right? Okay. And I told you that I cannot replace this by spectral norm. That's correct, but what's true is that can be replaced by epsilon times Frobenius norm times the spectral norm. So one of the Frobenius norms can be replaced by spectral norm. Now this looks just like an improvement going to another norm. It's not. This is a theorem due to Rudelson, which came about, maybe 5-6 years after the original paper, then after our paper. But this uses a nice bit of function analysis. It's not simple. There are slightly simpler proofs of this, but it's still not simple. Now, this turns out to lead to a bunch of things. probably the most important thing is graph sparsification. And I'll tell you the result but not prove anything. This is due to Spielman and Srivastava. So you need the fact that one of the Frobenius norms has gone to spectral norm to get graph sparsification. So graph sparsification says the following. I give you any graph GBE. From that, I can produce a graph. This is n vertices. I can produce a graph H, which is a subgraph of G. I'll write it like this. So H is on n log n vertices, sorry, n log n edges. And has the property that every cut in H is roughly same as every cut in G. So for any cut S vs the weight of edges across the cut in H, weight of edges across S V minus S in H is within 1 plus or minus epsilon of the same thing in G. Okay. So it's a purely graph theory result. So what it's saying is I can produce a much smaller graph so that there are exponentially many possible ways of cutting the graph into two parts, right? Any subset of vertices, any subset of vertices. H, without fail, for every cut, has about the right number of edges as G does. Okay? I mean, that's completely non-trivial. I mean, it requires quite a lot of work. But central to that is Rudelson's theorem. Rudelson's theorem is also about length squared sampling. So can we replace this for just length squared sampling? So this, I won't be able to prove that, but hopefully I've stated the result well enough for you to see. So what is interesting is, of course, that this is a purely combinatorial result follows from this matrix kind of stuff, right? Not terribly surprising. A lot of graph problems are related to matrices, but it does follow from that. The bound today I showed is also got spectral norm on the right-hand side, but the matrix multiplication bound, for instance, had only the Frobenius norm. That can be replaced. So, okay, so maybe I should say more specifically, we wanted to multiply two matrices A and B, A and A transpose, let's say. So A and A transpose minus our estimate. Okay. Even if I wanted to bound the 2 norm, the right-hand side was only the Frobenius norm. What Rudelson proves is that for that specific bound, so it was not precise enough, for this specific bound, that I want the spectral norm of my error of the product is bounded by one Frobenius norm once. You still can't get rid of this. It cannot be purely spectral. The centroid thing is for Frobenius. Yeah, you're right. Centroid thing is not for spectral. Actually, there's some interesting open questions there, but no, this is only for Frobenius so far. If the rows of A were picked from an IID distribution, right, then you would probably want to center out by subtracting the mean. The mean is just the average of the rows. It's a very good estimate of the mean because you've got enough samples. Then you subtract it out. Then, as he said, then the AA transpose would be the variance covariance matrix. A transpose A. AA transpose would be the variance covariance matrix. So, so I think I mentioned this once. The original motivation for all these sampling results basically came from trying to estimate the variance covariance matrix of distributions. So you would subtract out the center. There are cases where you don't want to center data. I probably don't, I mean, there are some PCA examples where you don't want to center data. But certainly, IID picks, you want to center data, likely. Yeah, sometimes you want to keep the data non-negative. That's another example. Non-negative matrices come up, then you don't want to center it. It'll introduce negatives. the theory only gives you bounds on R that are very large, right? And the question is, can we get lucky with smaller R? I think there are empirical studies, but I don't know. Theoretically, the epsilon, well, if you want an epsilon of 0.01, there's an R which is 1 over epsilon to the 4th power or something. So that would be 10 to the 8. You don't necessarily want that. That will be bigger than the whole matrix. But you hope empirically smaller R will work.